An automated procurement system approves a contract action based on a machine learning recommendation. 6 months later, an inspector general review flags the action as potentially non-compliant. The program office needs to reconstruct exactly what the system knew at the moment of recommendation, what knowledge sources it drew from, which rules it applied, and who last updated the relevant policy assertions in the knowledge graph, and when any of those assertions have since been superseded by updated guidance. The system can show the recommendation. It cannot show the reasoning. The audit fails, not because the decision was wrong, but because the decision cannot be proven right. That distinction is the difference between a defensible automated system and liability. This is Provenance, Traceability, and Auditability in Machine Learning, ML Part 23. Why knowing what your system decided is worthless if you cannot prove why it decided it, and whether the reasoning is still valid. We covered monitoring in Part 6 as the operational practice of detecting when machine learning models degrade. Provenance, traceability, and auditability operate at a different layer. Monitoring asks whether the system is still working correctly. Provenance asks whether the reasoning behind any specific output can be reconstructed, validated, and defended at any point after the fact. Section 1. What provenance actually means. Provenance in knowledge systems is a record of where a piece of information came from, who asserted it, when it was asserted, under what authority, and what transformations it has undergone since its origin. It is the chain of custody for knowledge. In a machine learning system operating over a knowledge graph, provenance attaches to every triple. This asset was classified as mission ready by the maintenance management system at a specific timestamp based on an inspection record authored by a specific technician under a specific certification authority. Provenance chain is itself stored as triples, which is where Provo, the W3C provenance ontology, becomes directly relevant. Provo defines a standard vocabulary for representing provenance as RDF triplets. Entities are those things whose provenance is being tracked. Activities are the processes that used or generated those activities. Agents are the people, organizations, or systems responsible for activities. Those three concepts and the relationship between them cover the provenance requirements of most production knowledge systems without requiring custom provenance schemas that can't interoperate with external auditing tools. The practical implication is that provenance in a properly architected semantic machine learning system is not a separate logging layer bolted on for compliance purposes. It is native to the knowledge representation. Every assertion carries its provenance. Every inference carries a record of the assertions and the rules that produced it. The audit trail is the knowledge graph. Section 2. What traceability actually means. Traceability is the ability to follow machine learning output backward through the reasoning chain to the source data that grounded it. The provenance asks where knowledge came from. Traceability asks how a specific output was produced from that knowledge. In systems combining machine learning models with knowledge graph reasoning, traceability requires connecting three layers. The output layer records what the system recommended or predicted. The reasoning layer records which knowledge graph assertions and entailment rules were contributed to that output. The source layer records the provenance of each contributing assertion back to its origin and operational data, external knowledge sources, or human expert input. A fully traceable machine learning recommendation looks like this in practice. The system recommended rerouting a shipment. That recommendation was produced by a model whose top contributing features included a customs delay triple, a weather advisory triple, and an alternative route capacity triple. The customs delay triple was asserted by an automated feed from a border agency system at a specific timestamp. The weather advisory triple was asserted by a national meteorological service feed. The alternate route capability triple was entailed from the current load assertions using a routing ontology rule last validated by a logistics domain expert on a specific date. Every link in the chain is reconstructible. An investigator following the traces does not need to trust the system summary of its reasoning. They can verify each step independently against the source assertions and their rules that connect to them. RDF star, introduced in RDF 1.2, which we briefly mentioned in Part 18, makes this traceability architecture significantly cleaner than earlier RDF implementations required. By allowing triples to annotate other triples directly, RDF star eliminates the verbose reification patterns that made provenance-aware knowledge graphs expensive to build and query in earlier versions of the standard. Provenance metadata attaches to assertions at the triple level without creating intermediate nodes that complicate query logic and inflate graph size. Section 3. What auditability actually requires. Auditability is the operational capacity that provenance and traceability enable. It means that any output the system has ever produced can be reconstructed on demand with its full reasoning chain, that the reconstruction reflects exactly what the system knew at the time of the original output rather than knowing what it knows now, and that the reconstructed chain can be presented to an external reviewer in a form they can independently verify. The temporal dimension of auditability is the hardest requirement to meet in practice. Knowledge graphs change over time. Assertions are updated, superseded, or retracted. Ontology rules are revised. New knowledge sources are added. An audit conducted 6 months after decision needs to reconstruct the state of the knowledge graph at the moment of that decision, not its current state. This is a point-in-time query requirement that feature stores address for machine learning training data, which we covered in Part 4. At the semantic layer, the same knowledge requirement applies to knowledge graph state. Versioned knowledge graphs that preserve historical assertion states with timestamps allow point-in-time reconstruction. Append-only triple stores that never delete superseded assertions but mark them as historically valid within specific time ranges are a common implementation pattern for systems with strict auditability requirements. The second auditability requirement is interoperability to non-technical reviewers. A chain of SPARQL queries and RDF triples is technically complete but practically opaque to an inspector general, a contracting officer, or a regulatory examiner. Production auditability systems generate human-readable audit reports from the underlying provenance graph, translating formal knowledge representations into natural language summaries that non-technical reviewers can evaluate without understanding RDF. The formal record exists for technical verification. The natural language summary exists for human judgment. Section 4, where provenance systems break down. Provenance completeness is the most common failure. Systems track provenance for some assertions but not others, creating gaps in the audit chain that surface under investigation. A machine learning recommendation that draws from 3 knowledge sources, where 2 have complete provenance and 1 does not, produces an audit trail that is mostly complete and entirely inadequate for regulatory purposes. Provenance must be comprehensive, or it produces false confidence. Provenance freshness conflicts with performance. Attaching a provenance metadata to every triple in a large knowledge graph adds storage overhead and query complexity. Systems under performance pressure cut provenance coverage to reduce costs. The cuts are invisible until an audit reveals that the assertions that mattered most for a contested decision are exactly the ones without provenance records. Agent attribution at scale is generally hard in automated systems. When a machine learning pipeline asserts thousands of triples per second based on automated inference, attributing each assertion to a meaningful response agent requires architectural discipline. Saying an automated pipeline generated an assertion is technically accurate but operationally unhelpful when an auditor needs to know who is accountable for the knowledge that drove a consequential decision. Production systems need clear agent hierarchies that map automated assertions back to the human authorities who designed them, validated, and approved the pipelines that produced them. Section 5, why this matters. Machine learning systems that cannot demonstrate provenance, traceability, and auditability will not survive contact with regulated procurement environments, defense program offices, or any operational context where decisions carry legal, financial, or mission consequences. The capability of the model is irrelevant if the reasoning behind its outputs cannot be reconstructed and defended. This is not a feature compliance requirement to plan for eventually. It is a current operational reality in the domains where semantic machine learning infrastructure delivers the most value. Building provenance, traceability, and auditability into the architecture from the beginning costs significantly less than retrofitting them onto a system that was designed without them. In Section 24, we close the semantic layer arc with a look at the standards and frameworks that formalize these requirements into implementable specifications, and why the choice between automated and manual ontology construction determines whether semantic infrastructure scales or stalls.